Gibbs Duhem equation, and I'll talk about this perhaps tomorrow or Friday. Okay. So better not attempt this. So now, how do I define this partial molar volume of any substance? That is what I did. I took a large amount of ethanol and I dropped a very small amount of water in it. So that is the change in volume as I change the number of moles of water, or when I add a small amount of water, what is the change in volume? So I could write it mathematically like this: del V by del N. Now I don't change the pressure, I don't change the temperature, I don't change the number of moles of any other material. Yeah, and that's why I said a large amount of ethanol, because for that small amount of water when it comes in, it doesn't change much. So every other species is held constant. N prime is for every other species. I'll just denote it by Vj, or then I could write Nj. Yeah, it's fine. Jth component, let's say. Yes? Which is added. V is the total volume, right? Vj is the partial molar volume of jth component. Thank you so much. We should. Partial molar volume of jth component. Dn. Well, I at least have to be dimensionally consistent. No. That would be dV. That would be the change in volume. So let's just leave it. That's just the partial molar volume. Okay. Because it's molar volume, I'm still dimensionally consistent. This is the total volume divided by the number of moles. Huh? V is not molar. V is the total volume. Right? Well, we could just write that over there, right? Thanks. Okay, so that's how I define my partial molar volume. Now, if this partial molar volume, if you think of two different components, A and B, then one of them would have a partial molar volume which is by Na, holding pressure, temperature, and well, instead of n prime, I could even write. Yeah, please, just one moment. We'll finish it. No more. So the change. Now, if I wish to see what is the total change in volume, I could see it like this: plus the partial molar volume of Nb, pressure, temperature, Na. Right? So the change in volume times the number of moles that are change in volume with respect to V, the number of moles. These equations are somewhat analogous to what you've seen earlier when we defined du, dh, dg, dA, everything. And you see that these are at constant pressure and temperature. So and we've been trying to deal with the chemical potential. So the chemical potential also analogously would have something similar. We'll come to that in the next lecture. But if you think of the chemical potential at constant pressure and temperature, then all I'm worried about is additional work being done over here. Right? At constant pressure, that's what we found in one of the lectures. That dG at constant pressure and temperature is equal to work additional Maxwell. Okay. So we meet on Friday then, huh?